Based on ionization processes discussed in previous lessons, we will move on to study the plasma of an electric discharge. In high voltage technology, plasma can be an undesirable phenomenon, leading to emergency motors and equipment failure. However, plasma is often specially created and serves as a switching element or technological medium. Plasma is one of the fundamental states of matter and was first described by chemist Irving Langmuir in 1920s. It consists of a gas, ions and free electrons. Plasma can be found not only in the form of electric discharge, but also in the form of flame of an exothermic chemical reaction, a nuclear fusion or fission reactions, in the form of laser spark, that is a substance ionized by laser radiation. Plasma also is convenient to represent charge carriers in solids. Huge areas of outer space are filled with plasma. All these very different objects have much in common and are often described by the same physical equations. By plasma, we mean a gas in which a significant part of the molecules is ionized. Plasma may contain space charge regions. Otherwise, the plasma is quasi-neutral. That means the number of positive and negative charge carriers is the same, and the plasma as a whole does not create an external electric field. Also, it may distort it. Plasma is electrically conductive and reflects electromagnetic waves. Therefore, switching high voltage and lighting protection with powerful laser beams is very difficult technical task. The photo shows the switching of a pair of electrodes located at a distance of 8 meters from each other, with a voltage of about half of million volt by a powerful laser beam. This is physical experiment done in a high voltage laboratory and a pretty record-breaking achievement because plasma reflects light. It is opaque and creates a shadow behind it. This makes photoionization in the shaded area impossible and does not allow easy switching of high voltage by a laser beam. But by the way, laser switched discharges exists, and it may be used in high voltage technique, and we done it many times. Shown here are the temperature ranges of different types of plasma. So 10 power 7 to 10 power 8 Kelvin is high temperature plasma. It may be produced only at nuclear reactions. And 1000 at 10 power 3 to 10 power 4 Kelvin is low temperature plasma. All other cases of producing plasma. You see, 10 power 4 or 10 thousandths of Kelvin is low temperature plasma. To maintain the plasma state, some rather high concentration of charged particles is required. Otherwise, the plasma will spontaneously turn into a gas in a short time due to energy dissipation caused by recombination and diffusion. We will see about this process. Recombination of charged particles is a reverse ionization process. The slide shows the reactions of electron, ion, and ion recombination. In both cases, the released energy is carried away by electromagnetic quanta, h nu. As a rule, this is radiation of the optical and ultraviolet range. So energy released during recombination is carried away by photons. In natural plasma, the concentrations of positive and negative particles coincide. You may see n plus and n minutes will mark this concentration, and it equal to n0. Otherwise, over time recombination decreases this number n. You may see this formula. Please write it down if you have your notebooks. The t is time in seconds. Rho is the recombination coefficient, cubic centimeter per second. Under normal condition for air, rho, so recombination coefficient, is 2 multiplied by 10 power minus 6 centimeter cubic per second. Let's solve a simple problem with this expression in order to estimate the characteristic lifetime of a plasma without an energy source that supports ionization. Let's assume the concentration of ions in the gas discharge channel n plus equal n minutes, so natural, and equal to 10 power 11 ion per centimeter cubic. Assume that there is no current in the discharge channel. So calculate the time during which this concentration decreases by 2 times. I advise you to get a working formula first. To do this, first express the ratio n0 divided by n from the expression, and then express the time t from the resulting equation. You may see it here. So we divided left and right part by n and multiplied by the denominator of right part. So we have this equation, and here we express t from this expression. Consequently, by the condition of the task, n plus equal n minutes and equal to 10 power 11 ion per cubic centimeter, and n0 divided by n equal 2, because concentration decreases by 2 times. So when we substitute numbers to this formula, we have time is 5 microseconds. So 5 millionths of second will be time when concentration of ions decreases 2 times. That's a short period. Let's consider mobility of positive and negative ions. As you know, in an electric field, a Coulomb force acts on charged particles. Due to collisions with molecules, the acceleration will not be constant, and the particle moves at an average speed, v, equal proportional to strength of electrical field with some coefficient k. So this is similar to how the speed of a skydriver changes during a jump. At first, it increases almost linearly in proportion to the acceleration of gravity. Then, when air resistance becomes significant, comparable to the weight of the skydriver body, the acceleration decreases. Finally, when weight and resistance cancel each other out, he moves at constant speed. This speed is proportional to some parameter, which depends on the body weight and the posture in which the fall occurs. The mobility of ions and electrons in a plasma plays the role of this coefficient. Under normal conditions, the mobility of positive and negative ions in air is next number, 1.6 and 2.2 centimeter per second divided by volt per centimeter. Electrons' mobility at strength more than 100 volt per centimeter and normal conditions is 5 multiplied by 10 power 3 centimeter per second per volt per centimeter. Note that the electron mobility is much higher than the ion mobility, maybe 3 or even more orders of order of amount. Let us solve the next task. There are very simple calculation examples. I suggest solving them in order to evaluate and remember the orders of magnitude that are used in them. This helps to better understand the processes in high voltage equipment. Task is calculate the distance that ions travel in air under normal condition for time 5 milliseconds in an electric field with strength 5 kilovolt per centimeter. We substitute numbers in formula, which I hope you remember, and have these numbers. So, ions move at speeds of several tenths of meter per second, or that is the same several hundreds of kilometers per hour. And negative ions are 1.5 times faster than positive ones. Let me remind you that the electrical strength of air under normal condition is 30 kilovolt per centimeter. So the intensity for which we carried out the calculation is not too large and is quite common in existing electrical installations. Next, we calculate the distance that ions travel in such an electric field for a time of 5 milliseconds. That is, for a quarter of the period of standard alternating voltage of industrial frequency 50 Hz. So you see that is get the order of decimeters. Now let's consider diffusion of the charge carriers in plasma. In addition to movement under the influence of electric field E, charged particles due to diffusion caused by thermal motion move from regions with a higher concentration to regions with lower concentration. The rate of such diffusion is greater the temperature and the greater the concentration gradient. Diffusion of particles in plasma is characterized by so-called diffusion coefficient, D. The coefficient of proportionality between the particle flux, the product of concentration of particles, by their average speed of directed motion. Through a unit area per unit of time and the concentration gradient of particles in the direction perpendicular to the selected area. So gamma is particle flux, and dN by dx is x component of concentration gradient. Diffusion plays a significant role in expanding the channel of electron avalanches, which we discussed previous our lectures. Next question is ambipolar diffusion. If the plasma is isotropic and weakly ionized, electrons, due to their higher mobility, diffuse faster than ions, as a result of which a quasi-static electric field of charge separation arises. It leads to a decrease in the diffusion rate of electrons and an increase in the diffusion rate of ions, so that their diffusion rates are comparable. This diffusion process, in which the quasi-neutrality of plasma is maintained, is called ambipolar diffusion. The presented expressions make it possible to determine the particle fluxes or which is the same the current density for electrons and ions during ambipolar diffusion. The first component of these equations represents drift of particles upon resulting electrical field. This resulting field is a superposition of external electrical field and field caused by separation of charges due to a difference in mobility of electrons and ions. The second component of these equations represents diffusion current density. For quasi-neutral plasma, the density of ions and electrons is the same, and the fluxes of electrons and ions are the same. Then the field strength in the previous formulas, which is electric field caused by ambipolar diffusion, can be expressed by this equation. Bye for now, for next our lectures.